Okay, hello everybody. Today we're going to look at what's called the method of initial rates. Okay, this is a way to calculate what's known as a differential rate law. All right, differential rate law is a lot of times referred to just simply as a rate law. So we're just going to call this just a regular general rate law. So if it doesn't say integrated rate law, you're going to be finding the differential rate law. Now if you remember back to what I said before, a differential rate law shows how concentration changes the rate. So there's a connection between rate and the concentrations. And it's going to be illustrated between this equation, rate is equal to K, which is some sort of constant, A, and the concentration of B. Well, we're going to try to find our N and N. That is an N. Okay, M and N, and those are the order of reaction. M and N are orders of reaction. Okay, what it simply means is how does A change the rate? Will it not change it at all and be a zero order reaction? Will it, if it doubles, will the rate double? If it does the same thing, like if I double this and this, the rate doubles. If I triple the concentration and the concentration triples, the rate triples, then therefore it's first order. If I double the concentration, and the rate quadruples, then I know that it's a second order. Okay, so that's what I'm looking for, is how does a change in concentration affect the rate? And here we're using the method of initial rates. So how are we going to do this? Well, we're going to look at these reactions. These are three different experiments that are done. In this experiment, they had the concentrations equal to each other, and this was what the rate was initially. Okay, so they let this reaction go and they calculated back to what are known as the initial rates and the initial concentrations. What we're going to do is we're going to compare two experiments. We're going to compare experiments 1 and 2, and what we're going to do is we're going to look at the effect of concentration of A by doing that. Remember, what we're solving for is rate is equal to K, A, M, B to the N. So what I'm going to solve for here essentially is M. Okay, so it's the effect of A. So what I'm going to do is I'm going to do experiment 2 and compare that to experiment 1. So what I'm going to do is I'm going to take the rate of experiment 2 over the rate of experiment 1, which is equal to some K, A, M, 2, B, and 2. So what I'm going to do is I'm going to take the data from experiment 1, plug it in down here, and experiment 2, plug it in here. Now if we look at this, we can see right away that the K's are going to drop out, right? Because it's a constant, it's going to drop out. Now in experiment 1 and 2, these were the same, so these would drop out. So essentially what I'm going to do is I'm going to take my rate of 2 and 1, plug them in here, my concentrations of A, and plug them in here, to the M power. Okay, it should be pretty obvious what's going to happen here. This is 2. This comes out to be 2, the M power, and it's pretty obvious, hopefully, that M is equal to 1. So we say that this is first order with respect to A. So therefore up here I can rewrite my rate is equal to K A to the first power. What I'm going to do next is solve for B. Experiment number 3 to experiment number. So here's where these are changing. These are staying. This is how I'm choosing this. I want A to cancel out, so the concentrations of A are held constant here, and in B they're held constant here. So I'm looking at these two experiments. Oops, I said 1 when I meant to say experiments 2. Okay, so let's throw these numbers in here. Rate of 3 over the rate of 2. Make the numbers work out nicer. Pick the higher number as the one to put on the top, and the lower one is the one to put on the bottom down here. Rate K, A to the first power, B to the n power, and this would be for experiment 3, and K equals A first power, and that would be for experiment 2, and B to the n and 2. Alright, as you can see, K cancels, A is going to cancel, A is going to cancel. That leaves us with the rate of 3, which is 16. Here you're going to have 4. Here you're going to have 2 to the n, and n is equal to 2. So we say that it's second order with respect to B. So therefore 2 here. And the overall order is third order. Overall order equals 3. Okay, so first order with respect to A, second order with respect to B. And that's how you use the method of initial rates to solve for your orders of your reactants. Now if you wanted to solve for K, if you had to, you do K equals rate over A to the first power and B to the second power. And you can solve for K. I'm not going to do that because I'm going to save some time here, but that's pretty much it. So thanks a lot. If you have any questions, let me know. See you later.